So let's resume our design here. We were in the stage where we want to change the constellation points. As you can see right here, there are many ways to represent these constellation points. We can represent them directly on the axis, or also we want to have them right here, we can put them every 90 degrees starting from 45 degrees, then 135, and so on. So to do this, what we have to basically do is to assign the polar or the real or the imaginary part of every angle, or to write the angle in polar code by saying that this first component, the constellation diagram, is going to be located in 0.7 jot. That represents this 1. Then what we have to do is to go to the negative x-axis or real part, and we are going to set same values and 0.6. Then both of the negatives components. And finally, this component that is going to be the positive real part plus negative imaginary part. And yes, so we continue, and now that we connect our block, basically what we have is that all the blocks, or that we have, at least the random source and the constellation modular, don't present any trouble at all. It is important to mention right here that the constellation modulator it uses a constellation object and other settings to control the transmitted signals. As I mentioned before, it determines how the symbols are encoded and expects values as input values bytes, and as the output is going to generate the encoded baseband signal. And it uses a root raised cosine pulse shaping filter that is going to give us some parameters to adjust the roll-off factor. So apart from the throttle, basically what we are going to do now is to add the building block of the channel. And to do this, we can search here what are the channel models that we currently have. And yeah, so here we set our block, we connect them, and here what we have to do is to assign the values that it has by default. So as you can see here, the values that we can modify are the noise voltage, because when we transmit signals into a medium, there is white noise, and for instance, in our case, we are going to establish a really small voltage for this noise of -6, and the offset, the frequency offset, basically the frequencies are generated by oscillators. So it is going to be really common that we have offset, but in this case we are just doing a simulation. As a consequence, we are going to establish this, we are going to set this value as 0. And here, when we start to read what is epsilon, we find out that the epsilon is the sample timing offset to emulate the different rates between sample clocks of the transmitter and receiver. One is not different. So in this case, what we are going to say is that our transmitter and receiver are completely uh, they are completely synchronized, and as a consequence we are going to establish this value as 0. Yeah, let's see what else we have here. We have tabs that we are going to discuss in the next block, but until now we are going to set tabs as 1. Basically, this value is tabs is normally used to so to represent, so when we are transmitting signals using, for instance, air, there is multipath, and in the receiver side the signals arrive at different times. It depends how long the path is, so the path that the signal takes to reach the receiver, and this effect generates interference. And a way to model this interference is through this value called tabs. As we can see right here in the documentation, tabs of a FIR filter to emulate the multipath delay profile. And then we have the noise seeds, random number of generator of seed for the noise source, that in this case we are going to set as 0 as well. So let's go into continue with the implementation of our transmitter, and in this stage what we would like to see is what is going to be the output until now that we can generate with the current setup that we have. So and to do this, let's go to check using different blocks. For instance, let's go to use time sinks, Qt time sinks. We are going to check also what are the constellations that we have, and what else we can add right here. We are going to see the response in time. We are going to see the constellation, and instead of using this Qt GUI sync, what we can do is to check what is the frequency of the current setup that we have right here. So I'm going to connect all those blocks together, and let's go to see what is going to be the outcome that we are going to have. As you can see, as we don't have any errors, so this button, with this button, what we are going to do is to generate a flow graph. When we push on this button, or we click on this button, so basically here where we have our folder, we are going to generate a Python file. And this Python file, what it's going to do is to describe every component of our design. So as we can see here, we have to see our generators, yeah, here what we can see is, for instance, we can see here the throttle that we are using, the constellation modulator that we are using right here, and the other components that we have inside. And as you can see here, we have the Qt time sync, the Qt frequency sync, And we have also the constellation that we are going to see when these blocks are executed. So far so good. So let's go to um, implement. So let's go to execute this flow graph. Good. As you can see right here, this is the modulated signal, and as it is expected, this modulated signal has two components, the imaginary and the real components, as we have already seen from our explanation right here. So basically, this is the reason why we call this kind of modulation quadrature phase key shifting, because we have two components, two signal components, in phase and in quadrature. Here what we see is the frequency that we have in the until now. So this is the frequency response, and as you can see right here, the constellation points or the constellation diagram looks really bad. So it's not really appreciable that the transmitted signal that we want to achieve, there are only 4 points right here, is clear. So we have many points in our implementation. So in the next block, what I'm going to show you is how we can really correct this kind of imperfections to make transmission with completely defined constellation points. So to do this,